Hi, we are going to start a journey through more abstract and more powerful theorems and more theoretical stuff. The first step of this journey will be a simple reminder of the weak law of large numbers that we can prove using a finite second moment if we have that. Assume that we have x1, x2, x1, x2, x3, and so on IID random variables with mean, finite mean EXI equals to mu, and that's all we need really. So then for any p, any delta, sorry, any epsilon, let's call it epsilon, any epsilon positive, we have that the probability that Sn over n minus mu is more than epsilon in absolute value goes to 0 as n goes to infinity. And I also need to tell you, well, what Sn is. Sn is the sum of the first n of the xi's. Okay, so that's the weak law of large numbers. People abbreviate this sometimes as WLLN, weak law of large numbers. So if you have a sum of IID samples and you take that sum, you divide by n, it will converge to mu in this sense that the probability they deviate from the actual mean of the xi's is more than epsilon for any fixed epsilon goes to 0 as n goes to infinity. This is called a weak law because, let me just mention here that the strong law of large numbers will say that Sn over n converges to mu with probability 1. Almost surely, or with probability 1. So, okay, so equivalent way of writing probability Sn over n goes to mu is 1. That will be the strong law. Okay. We are going to cover later on what the difference is between this kind of convergence and that kind of convergence, why it's called weak, why that's called strong. And we are going to prove the strong law, which implies the weak law. But for now, what I want to do is give you a simple proof of the weak law assuming a second moment. So I'm going to give you a proof if the variance of the xi's, which I'm going to call sigma square, is also finite. Okay? Notice that the theorem does not require that. The theorem is true without this assumption, and to prove that, we're going to have to work a little bit more. But a simple proof is available actually from probability 1, you might have seen this before, if the variance is finite. And it goes like this. So if I look at this variable Sn minus n, Sn over n minus mu, this random variable, well, let's concentrate on Sn over n. Sn over n has mean the sum of the mu's, which is n times mu, because Sn contains n of these xi's, over n, so that's mu, and it has variance 1 over n squared times the variance of Sn, because of this constant that comes out as a square. Because of the independence property, the variance is added up. So under the assumption of a finite variance, we have here n times sigma square, so that's sigma square over n. And all we need to do here is apply Chebyshev's inequality, which is a version of Markov's inequality for squares, and that tells me that, so Chebyshev's inequality tells me that this is smaller than or equal to the variance of Sn over n over whatever bound I see here squared. So this is going to be epsilon squared. And the thing is to plug in the variance from here, and notice that this will go as n goes to infinity to 0 for any fixed epsilon. Okay, so it's as simple as that, for under the assumption that we have a finite variance. Let me show you a corollary, an example of this, or a corollary of that. Corollary. Okay, so this is now proof, right? We just put that here. So corollary, if xn is binomial, let's not put the n down here, let's put the n up here, is binomial of parameters n and p. P is fixed, very important, P is fixed, it's not going to 0 as before in the Poisson approximation. This is fixed now, okay, and n goes to infinity. Then in the limit what we have is that the probability that this binomial random variable over n minus p is more than epsilon converges to 0 as n goes to infinity, and this is true for every epsilon positive. Okay, and the reason is, if you want proof, is that xn is equal in distribution to the sum of n IID Bernoullis. These are IID Bernoulli p's. Summing up n IID Bernoulli p's exactly gives the distribution of the binomial np. So they have each mean mu equals to p and finite variance, of course, they are 0, 1, so the variance is finite. So the above proof applies, but in fact even without a finite variance the weak law of large number applies. And so all that happens here is just actually I can even call this Sn, the index was down here, the sum of the IID random variables. That's what we call Sn in the top of the page, okay? And the mean is P. The mean is P, so that's what we called mu before. So Sn over n minus mu now becomes exactly xn over n minus p. Other than that, everything matches. We have IID random variables with a finite mean and even a finite variance, but that's only needed for this proof. So the statement translates to exactly this statement here. So the binomial random variable, if you divide that by n, converges to p in this weak sense.